Welcome to our first mini lecture of week number 3. This week we will be talking about radiation. In this first mini lecture we'll be talking about the properties of radiation. Electromagnetic radiation is more commonly known as light. In everyday parlance, the term radiation carries negative connotations and is to be avoided because it is harmful. However, radiation really just means something that emits or radiates from a source. And there are different types of electromagnetic radiation, which we will talk about in mini lecture number 2, but most of it is not harmful. Electromagnetic radiation is important in astronomy because it is the only way we have to get information from other stars. Everything outside our solar system is way too far away to ever hope to visit with our current technology. But light, coming at the speed of light, is able to bring us a lot of information. And so we need to understand light before we can understand what that light is telling us about other objects in space. You may have heard that light can be thought of as either a particle or a wave. For now, we're just going to talk about light as a wave. So waves have some properties, and on this slide we are going to go over the vocabulary describing the properties of waves. The first property is the wavelength of light, and this is denoted with a Greek letter lambda. Wavelength is the distance between the peaks of adjacent waves. So if you're out on the ocean, such as in this picture, the distance between those two waves that are coming in, between the tops of those two waves, that would be the wavelength of these ocean waves. And every type of wave, whether it be an ocean wave or a sound wave or a light wave, can be defined with a wavelength. Our next definition is for the word frequency, which is denoted by the Greek letter nu. Here it looks sort of like a little script V, but that's really a Greek letter nu. And frequency says how many times a given point will go up or down every second. So let's say that you are out on the ocean and the waves are coming by one every 10 seconds. You will go up and down once every 10 seconds, or in 1 second you will go 1/10 of the way up and back down. So we would say that the frequency of ocean waves would be 1/10. The unit that we use for frequency is hertz. Hertz, H-E-R-T-Z, just means 1 per second. So the ocean waves we were just talking about would have a frequency of 1/10 hertz. The final vocabulary word used to describe waves is the amplitude. Now the amplitude is similar to the height of a wave, but we're going to be specific and use amplitude to refer to half the distance from the bottom to the top of a wave. The bottom of a wave is called the trough, the top called the peak. So half of that trough to peak distance is the amplitude. For most types of waves, the wavelength and the frequency are related mathematically, and they're related through the speed of the wave. So for light, the wavelength and frequency of light are related by the speed of light, which we often denote with a little letter c, a lowercase c. So here are a couple of equations. Now I won't make you do detailed calculations with these, but I put them in because they show us a couple of important properties. The wavelength of light is equal to the speed of light divided by the frequency, or the frequency of light is equal to the speed of light divided by the wavelength. And because it's divided by the frequency or the wavelength, we have what we call an inverse relationship, which means that as the frequency is smaller, or in other words, fewer waves are passing us every second, the wavelength is longer. Or if the frequency is higher, the wavelength is shorter. Conversely, if we're talking about frequencies and using the frequency equation, a longer wavelength will get us a smaller frequency, or a smaller wavelength, a shorter wavelength, will get us a higher frequency. In short, what we learn from this is that if we know the wavelength of a light wave, then we can determine its frequency, or vice versa, if we know the frequency, we can determine the wavelength of that light. The speed of light, that lowercase c, is the same for all light, no matter what its wavelength is, what its frequency is, or what its energy is. The speed of light in a vacuum is 300,000 kilometers per second. And that's a universal constant. It doesn't change. If light is traveling through a vacuum, it moves at 300,000 kilometers per second. It doesn't matter whether we're talking long wavelengths, short wavelengths, small frequencies, large frequencies, low energy or high energy. It all moves the same speed. The energy of light depends on its wavelength, and since we already know that wavelength depends on the speed of light, and the speed of light is the same for all light, we can also say that the energy of light depends on its frequency. And the relationship is given by these two equations. Now again, I won't make you do detailed calculations with these equations, but I put them here to show that if we're talking in wavelength, which is the first equation, the energy is equal to a constant of nature called Planck's constant, here it's the little h, times the speed of light, which is a constant, divided by the wavelength of light, which changes. So in other words, we have another one of these inverse relationships. If the wavelength is longer, then the energy will be smaller. If the wavelength is shorter, then the energy will be larger. The second equation gives the energy in terms of frequency, and you see here we have that energy is Planck's constant, so this constant of nature, times the frequency. In other words, if we increase the frequency, we increase the energy. Or if we decrease the frequency, we will decrease the energy. So let's summarize. Higher frequencies therefore mean higher energy, and higher frequencies also mean shorter wavelengths. Long wavelengths mean low energy. Long wavelengths mean smaller frequency, which also means smaller energy. So these three things, energy, frequency, and wavelength, are related to each other. One of the most common types of light, what you are probably most familiar with, is visible light. Here we have what we call a spectrum. A spectrum is where you spread light out into its component colors. And this is the spectrum of visible light, going from violet on the left to red on the right. And we also list here the wavelength of the light in nanometers. 1 nanometer is 1/1000th of a meter. And we see here that visible light has wavelengths between about 400 and 750 nanometers. And to give you a sense of scale, that's about the same size as a bacterium. Notice that the blue light, the violet and blue part of the spectrum, have these small wavelengths, whereas the red light has longer wavelengths. And since we know that longer wavelengths mean lower frequencies and mean lower energy, this tells us that red light is less energetic than blue light. Now, all of these move at the same speed, the speed of light, 300,000 kilometers per second. So the only thing that are different are the wavelengths, the frequency, and the energy. One other important side note is that the way that we plot a spectrum or show a spectrum in a picture, you always want to pay attention to the wavelengths, because sometimes we will put blue on the left and red on the right. Sometimes we will have red on the left and blue at the right. So be sure to look at the wavelength or the frequency or the energy, whatever we're plotting, to figure out which direction is blue and which direction is red. Let's take a little diversion and discuss how our eyes perceive color. It's not quite as straightforward as our eyes being able to determine the wavelength of light and therefore giving us a color. Here's a picture of an eyeball. In this diagram, light would come in from the left. It would enter our eyeball. It would pass through the lens and be focused on the retina at the back of the eyeball. Now, if you remember from biology classes or from elsewhere, our retina has several layers, but the two most important things in the retina for the purpose of seeing are the two types of cells, rods and cones. Rod cells do not see color. They only see how bright something is, while the cone cells are what allow us to see color. However, it's a little more complicated than this picture in that we have three types of cones in our retina. Each of those types of cones is sensitive to a different color of light. So we have some cones that are sensitive to blue light, some that are sensitive to green light, and some that are sensitive to red light. And this graph shows sort of the sensitivity of the different types of cones. And what you see is that there's some bit of overlap. So if green light comes into our eye, the green cones will see it the best, but the red and the blue cones will also detect it a little bit. If violet light comes in, the blue cones will definitely detect it. The green cones may or may not, depending on the exact color that's coming in. When we see color, the brain determines which cones have fired, which cones have detected light, and it's then able to combine that to determine the color of the light. So for example, let's say that we're looking at something that's yellow. The green cones and the red cones will both see that yellow light. The blue cones will not. And so our brains are able to combine that and determine that we are looking at yellow color. Now you may have heard of color blindness. Color blindness happens when one of these three types of cones do not appear in a given person. The most common type of color blindness, red-green color blindness, is very common in males, and it happens when the red cones are missing, so we only have green and blue. So people who have red-green color blindness are not able to distinguish between greenish and reddish colors. Another important point with the way that our eye perceives color is that our eye can be fooled. Let's say that I have a blue light and a red light both shining in. So the blue light has a wavelength of about 450 nanometers. The red light will have a wavelength of, say, 700 nanometers, and they're both coming into our eyeball. Our eye will perceive purple light coming into our eye, and that's what our brain will say, oh, this is purple that's coming in. But it is not purple wavelength light. True purple light has a wavelength of shorter than 400 nanometers, and none of that is coming in. So our brain has been fooled into thinking that there's purple when there really is no purple light. We take advantage of this with our computer screens, which have three colors of pixels, blue, green, and red. And by combining those pixels and making those pixels different brightnesses, we can fake our eyes into seeing wavelengths of light that aren't really there. So let's summarize what we've talked about in this mini lecture. First of all, we've learned that light carries information through space, and this is what makes it such a valuable tool for understanding distant stars and distant galaxies that we have no other chance of visiting. Light can be described as acting as a particle or a wave, and in this mini lecture we've talked about light solely in terms of acting like a wave. We learned some of the vocabulary associated with waves as well, in particular wavelength, frequency, and amplitude. We've learned that the wavelength and frequency of light are related by the speed of light, in such a way that long wavelength light has low frequencies, short wavelength light has high frequencies. We also discussed that all forms of light, no matter their wavelength, no matter their frequency, and no matter their energy, all travel at the same speed, and in a vacuum that speed is 300,000 kilometers per second. We learned the relationships between wavelength and frequency and energy and color. So long wavelengths mean lower frequencies. Lower frequencies and long wavelengths also mean smaller energies. And in visible light, the longest wavelengths and the lowest frequencies are the red light. Conversely, we learned that shorter wavelengths mean higher frequencies, and shorter wavelengths and higher frequencies both mean higher energies. And in visible light, the highest energy light is blue or even violet light. This completes mini lecture 1. You may now proceed and complete the response to mini lecture 1 before going on to watch mini lecture 2.